Let's talk about signals. Signals can be primarily classified into continuous time signals versus discrete time signals. Continuous time signals are mappings from real numbers to real numbers. That means a signal takes a real number as an input and puts out another real number as an output. As an example of a continuous time signal, let's look at x of t is equal to sine t. So x is a signal and it takes an input which can be any real number and the output will be a real number. So for example, we can see x of 0 would be 0, x of pi over 2 would be 1. And if you notice, the inputs can be any real number and the outputs are also in general real numbers. So let's talk about some examples. Note that all these examples are functions of time. So first example is speech. Let's say you want to record somebody's speech or sound signals. These are basically variations in pressure as function of time. You can talk about temperature at a given area or voltage between two wires on an electronic or electric component. And I'm sure you can think of many examples like that. So anywhere you're measuring a physical phenomenon which is changing continuously as a function of time and the time is changing continuously, that's a continuous time signal. A more generic case of continuous time signals would be complex signals. So far, we have been restricting the output of the signal to be real numbers, but we don't have to restrict the output to be real numbers. We can extend it to saying the output can be any complex numbers. So such a signal where the inputs are any real number, which we will usually interpret as time, and the output can be any complex number. So such a signal will be a complex signal. So let's look at an example of a complex signal. So let's take this signal x of t is equal to t plus j half t squared. So note that the input t can be any real number and the output is usually a complex number. So for example, x of 2 is 2 plus j2, x of 1 is 1 plus j half, and so on. So the inputs are always real numbers, outputs are complex numbers. Another example is a complex exponential. Like it's x of t is e to the j omega t. And using Euler's identity, we can write this as cosine omega t plus j sine omega t. Such signals are called complex exponentials because they're exponentials and they're complex signals. Now, as you can see, t can be any real number here, and the output cosine omega t is a real number, sine omega t is another real number. In general, this whole thing is a complex number, and this is the real part, this is the imaginary part. Sine omega t is the imaginary part, cosine omega t is the real part. Complex exponentials are something we'll be looking at a lot in this course because they are the foundations of Fourier transforms. In this course, whenever we say signal, the more generic case of complex signal is implied unless otherwise specified. Now let's talk about discrete time signals. What differentiates discrete time signals from continuous time signals is the input. In continuous time signals, the input is a real number, but for discrete time signals, the input is an integer. So discrete time signals are mappings from integers to complex numbers. That means the inputs are integers, outputs are complex numbers. Let's look at an example signal. X of n is equal to n squared. Now, note that this is a discrete signal, therefore the input must be integers. So you can plug in integers and you get real, in this case, you get real numbers as output. Note that x of 0.5 is not allowed because the inputs, so what goes into the input must be an integer. Another distinct point about notation here is if you notice for continuous time signals, we were using parentheses for inputs. For discrete time signals, we will use square brackets for inputs. This is how we will distinguish using notation between discrete time signals and continuous time signals. Note that in this case, the output is restricted to real numbers, but in general, it can also be complex. Let's look at another example. X of n is equal to e to the j pi over 4 times n. Using Euler's identity, we can write this is equal to cosine pi over 4 times n plus j sine pi over 4 times n. Again, notice that I'm using parentheses here because cosine and sine are continuous signals. But x itself is a discrete signal. Therefore, I'm using square brackets. And the inputs to x can only be integers. So I can plug in integers for n and get complex numbers. So for example, x of 0 would be 1, x of 1 will be this value. So let's look at some examples of realistic discrete time signals. So in continuous time signals, we talked about sound signals in general, which are variations of pressure, and they are continuous time signals. But let's say you take that signal and you sample it, then you get discrete samples. You can say first sample, second sample, third sample, and so on. So once you sample a signal, then it becomes a discrete time signal. Another example is an array stored in memory. Again, so an array will have indices. Let's say, for example, in C, indices start from 0, 1, 2, 3, and so on. In MATLAB, indices start from 1, 2, 3, and so on. So the index for an array can be considered as an input, and the output can be considered as the value stored in that location. So array will be a discrete time signal. Another example, daily records of someone's weights. Again, you can say your weight recorded on day 0, day 1, day 2, and so on. So these are all examples of discrete time signals. Note that the common feature among all this is that the input is discrete. And when an input is discrete, you can address it using integers. And the output in general can be any real number. And if you want to generalize even further, the output can be any complex number.